This is section 1.3a, analyzing graphs of functions and relations. By the end of this video, you should be able to use graphs of functions to estimate function values and find domains, ranges, y-intercepts, and zeros of a function. So to estimate function values, the graph of a function f is the set of ordered pairs x, comma, f of x, such that x is the domain of f. Basically, the graph of the function is the graph of the equation y equals f of x. So what it translates to in the picture is that for any x value that I can pick, so if x equals 1, then the associated height from the x-axis to the curve would actually be f of 1. So this is going to be f of 1. For example, I also have x equals -2. And so the distance from the x-axis to the curve would represent f of -2. And in more general, whenever I have any x-coordinate, that distance from the x-axis to the curve would represent f of x. And so the coordinates would actually be x comma f of x. So let's try an example. With more people turning to the internet for news and entertainment, internet advertising is big business. The total revenue R in millions of dollars earned by the U.S. companies from internet advertising from 1998 to 2008 can be approximated by the function R of t is equal to 17.7 t cubed minus 269 t squared plus 1,458 t minus 910 for the interval of 1, which is less than or equal to t, which is less than or equal to 10, where t represents the number of years since 1998. So we're going to consider this graph, and this is my graph here, and we're going to use the graph to estimate the total internet advertising revenue in 2007, and we're going to confirm that algebraically. So the thing that we have to consider is, well, what is going to be our starting point? Because I don't see the year 2007 on the x-axis anywhere for my independent variables, but I do see that it does represent the years since 1998. And so you ask yourself, well, if it's 2000, or if t equals 1 is going to be the year 1998, or sorry, t equals 0 is going to be the year 1998, going to be my starting year. I ask, how many years has it been since 1998 in the year 2007? And the answer is going to be 9 years. So I'm looking at t equals 9 is going to be 2007. And so I go over to my graph and I go over to t equals 9 and I trace it up and I see that it's somewhere between 3,000 and 3,500 on the graph, and it looks kind of close to 3,500. So I can say that R of 9 is approximately, and we'll say about 3,400. And so let's confirm that algebraically. So if I have 17.7, and I'm evaluating R of 9 now, and we're going to confirm it actually with the real data. That'll be 17.7 times 9 cubed minus 269 times t squared, or t squared, which is 9 squared, plus 1458, sorry, that's 58, 1458 times 9 minus 910. All right, let me grab that. And so we evaluate everything. So I cube the 9, I square the 9, I multiply everything out. So I know that 17.7 times 9 cubed minus 269 times 9 squared plus 1,458 times 9 minus 910 is going to be, when I actually get the real number, is going to be 3,326.3. Now, to interpret this answer, the total revenue, what I get, is in millions of dollars. So I'm really getting $3,026.3 million, which is actually $3.3 billion. Now let's use the graph to estimate the year in which the total internet advertising revenue reached $2 billion. So $2 billion would actually correspond with the 2000 line on the y-axis, because there's 2,000 millions in 2 billion. And so I'll trace the graph out, and I'll see that it hits somewhere around 6 years. And so what I can do is I can test it. And I also see that if I trace it out, I can see that somewhere between 6 and 7 years, I'm going to cross the 2 billion mark. So let's just confirm that algebraically. The way I'm going to do that is that to answer first, I'll say somewhere between 6 and 7 years after 1998, the revenue crossed the 2 billion mark. So to confirm it algebraically, we can just look at the graph and sort of just show that that at 6 years it was below 2 billion and at 7 years it was over 2 billion, because right now we don't actually have the tools in our bag to actually solve this equation for 2 billion. So I'm just going to show you that at r of 6 billion, or r of 6 years, it would be 17.7 times 6 cubed. Let me get my function again. Minus 269 times 6 squared plus 1458 times 6 minus 910. And then I'll show you what I get for r of 7. And what it should be is more than 2 billion, so 17.7 times 7 cubed minus 269 times 7 squared plus 1458 times 7 minus 910. And so when I evaluate those out, I'll take 17.7, multiply it times 6 cubed, cubed minus 269 times 6 squared plus 1458 times 6 minus 910, and I'll get 1977.2. And I'll do the same thing again for 7 years. And you get that it is 2186.2. So this represents 1.9 billion. So you can use the graph to find the domain and range of a function. If an open circle or a closed dot does not bound the function on either side, you can always assume that it continues beyond the edges of the graph. So for example, let's find the domain and range of this function. So a couple of things that I should note about this graph in particular. One is that let me see if I can get some writing happening here. Okay. There are a couple of things that I'm noticing here. One is that I see this dot on the end of the graph. Okay. That means that this graph starts at this particular x value. So it starts at x equals -8. And then I also notice that the graph continues going. And if I look at the graph, the arrow here means that this graph is going to keep continuing up and up and up forever. But it's also going to keep continuing out along the x-axis. So this graph is going to be defined pretty much everywhere along this x-axis on the domain, with an exception. Okay. The other thing that you should notice is that as you trace through the graph, you hit this hole in the graph. And so whenever you see an open circle in the middle of the graph, this is called a hole. It is also called a removable discontinuity. Removable meaning that I can kind of ignore that it's there, and it'll come into play when we talk about things like limits later in this unit. So basically, in order to write this domain, I'm going to start it at this at this x value, which is -8, and I'm going to continue it on forever, but I'm just going to take out this value at x equals 4. So essentially what I can say is that the domain of the graph starts at x equals -8, and it goes on forever, so that if I wanted to write it as an inequality, I could say that x is greater than or equal to -8, and that'll account for the graph starting at -8 on the x-axis and going on forever. But what I do need to do is I need to just exclude this one value that makes the graph undefined. So I will say that x can also not equal -4. So in order to use that in the domain, I'm just going to pull that over and use it in the domain and say that, sorry, I just grabbed the wrong thing here. Sorry. So I'll say that I have the set, or the domain of the function is the set x, such that x is greater than or equal to -8, but x can also not equal -4 in this, because that's what creates the hole in the graph. And since we're talking about domain of a function, x will be an element of the reals. Finding the domain of a function is probably one of the hardest things that we'll do in the beginning half of this year, and you can expect to have a lot of practice on it. In terms of the range of the function, the way that you always find the range of the function, which we'll call R for range, is that you always just look at the lowest possible y value, and then you look at the highest possible y value, and that becomes usually your interval. So if I look on the graph, I know that the lowest possible y value here is at y equals -9. Y equals -9. And then I look and I see, well, if I keep tracing the graph over and throughout the course of the graph, it does hit a maximum here at this point, it hits a minimum here, but those aren't the lowest points in the graph, and those are called relative maximums and minimums. We'll talk about that later in the unit. But if you continue going, this arrow just means that the graph is going to keep continuing up and up and up until it hits actually infinity. So I can actually write the range of this function one of two ways, either in set builder notation or in interval notation. Seeing as it starts at a specific point, and I know that f of x is going to be, or y is going to be greater than or equal to 9, since it's included in here, or the -9, I can actually just write this in interval notation and say that the range of the function is from -9 all the way up to infinity. So that means that every single point between -9 and infinity in the y-axis will be hit at some point throughout the course of this graph. Let's try these ones. So use the graph of g to find the domain and the range of each function. So again, for the domain, we want to go from, or we want to see where on the x-axis is this function defined. So I look on the left end of the graph, and it's always going to be from left to right. The graph is definitely defined at x equals -2, and the scale of this goes by 2, so pay attention. And then it looks like I see graph from everywhere between -2, and this value looks like x equals 6. And the thing you have to pay attention is that this 6 is not included in the graph because of the hole, or the removable discontinuity. Now, seeing as it's a very closed interval, I don't actually have to write it in set builder notation. I can just state that the domain of this function is going to be between -2 and 6, but not including the 6. So it's -2 in a bracket and a 6 in parentheses. And then the range of the function, I always start at the lowest possible y value, which for me looks like at 0, and it goes to the highest possible y value, which is going to be 4. So this is actually going to include the 0, so it's going to be 0 to 4. So let's try 2b. This graph is a little weird because it definitely has two distinct parts to it. This would actually probably be considered the graph of a piecewise function. So let's start with the domain of the function first. So a couple of things that I notice, I see removable discontinuities everywhere. So there's a removable discontinuity at x equals -4. I see a removable discontinuity at x equals 2. And another one down at x equals 2, but that's over the jump. This would also be considered something called a jump discontinuity. And I spelled jump wrong. Sorry, a jump discontinuity. Mostly because the graph jumps from one section to another, but we'll talk about discontinuity a little bit more later in the unit. But this is called a jump discontinuity. But in terms of the domain of the function, I know that in terms of the x values that this function is defined, I can say, well, I know that the function definitely exists between -4 and +2, but it doesn't exist at either one of these two, so I can actually write this as an interval. It actually is going to be easier to write this as the union of a couple intervals. So I know that from -4 to 2, this piece right here, the function is going to exist. So I know that from -4 to 2, the function will exist. But it doesn't include the -4 and it doesn't include the -2, so I'm actually going to put those in parentheses. And then also I know that from this value at x equals 2 here, and it keeps going on forever, and I know that it's going to keep growing and growing and going down the x-axis, so I know that it's also going to go from 2, and it's not going to include it, and it's going to keep going until infinity. And since it's two intervals together, I'm going to union them. And that is the domain of this function. It basically exists on a very small interval from -4 to 2, and then it's going to jump down and exist on another interval from 2 to infinity. Now the range is going to be a little bit more complicated. So the range of this function is going to exist at y equals or f of x equals 6, but then it's also going to exist at from 2 to -infinity. So I can pretty much try to write that as an interval. I know part of it is going to be from -2 to infinity, to -infinity, because this graph is going to keep decreasing and decreasing and decreasing. But the highest possible value that I can get is from 6 to 6, including. Okay, so it just includes the values at 6, and then it jumps down to -2 and goes down to infinity. Intercepts and roots. The point where the graph crosses the x and y axis are called the intercepts of a function. To find the y-intercepts of any function, you evaluate f of 0. In any function, there will be at most one y-intercept. So the graph will only ever cross the y-axis once. The x-intercepts, you can have multiple x-intercepts, and that will actually depend on a lot of things with the function, which we'll get to in Unit 2. So we're going to use the graph of each function to approximate its y-intercept, and then we're going to find it algebraically. So if I look at the first graph, I can assume that each one of these, the scale is going to go up by 1, and so I look at this graph, and I see if I want to find its y-intercept, that means it's going to be where it crosses the y-axis right here, and that looks like to me that it looks around 1 1/3. So I can say that this is approximately, or the y-intercept is approximately 1 1/3. So let's actually find that algebraically. So to find the y-intercept algebraically, you're always just going to evaluate f of 0. And when you find f of 0, that means that you're going to take -2 times 0 plus 4 all over 3. And f of 0 is actually going to be 0 plus 4 all over 3, which is 4/3, which actually works out to be 1 1/3. So the y-intercept is going to be at y equals 1 1/3. Similarly, we could do the same thing here. So if I look, it looks like the y-intercept of this function looks like 1, 2, 3, 4, 5. So this is looking like the y-intercept is going to be at approximately 5. In order to justify it algebraically, we're just going to find the intercept. So I could say, and did I say 5, 1, 2, 3, 4? Sorry, my fault. It is at y, at the y-intercept is actually going to be at 4. And so to verify it algebraically, we'll just say, or we'll evaluate g of 0, which is going to be the absolute value of 0 minus 5 minus 1. Well, it's going to be the absolute value of negative 5 minus 1. So g of 0 is going to be equal to 5 minus 1, which is 4. So that verifies it algebraically. So whenever you want to find the y-intercept of a function, you always evaluate f of 0 or g of 0. You essentially plug 0 into the function, and that will tell you the y-intercept of a function. The x-intercepts are called the roots of the function, and to find the roots of any function, you do it by setting f of x equal to 0. So to find the y-intercept, you plug in 0. To find the roots of a function, you set the equation or the function equal to 0, and you solve for the independent variable. So you're used to doing this with quadratics, but we're actually going to learn to do this with any kind of function this year. But to keep things simple, we're going to start with this function. F of x is equal to 2x minus, 2x squared plus x minus 15. So the first thing that I see is I'm going to estimate the roots of the graph, which are going to be right here and here. I do notice that my scale goes up by 2, so I can say that this is a little bit more than 2 and a little bit less than negative 2. This probably looks really close to 3. So this is approximately x equals negative 3. And this is, we'll say approximately 2.5. Since it looks like these don't cross the x-axis at a really nice point, I'm just going to jump right to it and use my quadratic formula to verify this algebraically. So if I remember my quadratic formula, to solve for 2x squared plus x minus 15 equals 0, because to find the roots of any function, we're going to take that function and set it equal to 0. Well, I know that x equals negative b, which is negative 1, plus or minus the square root of b squared, which is 1 squared, minus 4 times a, which is 2, times c, which is negative 15. I'm going to take that square root, and I'm going to put that all over 2 times the a, which is 2. So now let's just start cleaning it up a little bit. So you get negative 1 plus or minus the square root of, well, 1 squared is 1, negative 4 times 2 times negative 15, so this is negative 8 times negative 15. Negative 8 times negative 15, 120, so this would be plus 120, all over 2 times 2, which is 4. So x is really negative 1 plus or minus square root of 121 over 4. And something nice that we get is that 121 is a perfect square. So this is really just x equals negative 1 plus or minus 11 over 4, which breaks into 2 different roots. Negative 1 plus 11 over 4, and negative 1 minus 11 over 4. So negative 1 plus 11 over 4, well, that'll give me 10 over 4, which is approximately 2.5, or is 2.5. And then you get negative 3, or negative 1 minus 11 is going to give me negative 12 over 4, which is going to give me negative 3. So those are going to be my 2 roots of the function. And if you remember from Algebra 2 or from Algebra 1, if you want to write the roots of a function, you always put it in braces. So the roots of this function are actually negative 3 and 2.5.